Okay, let's look at this set of the paper, October, November 2020, paper 1, 2. Okay, let's look at the first question. So we have, this is a cubic equation, okay, and then we have got the value of the alpha, beta, gamma is equal to -1. First part of the question already asks us to state what is the value of the d. So basically for the value for the d here, it's already given that we have got this, okay, alpha, beta, gamma is equal to 1. So this value should be the negative d over a, okay? So that value of the d here should be just a 1. Okay, so in the part B here is to find the cubic equation. Then we have got like coefficients in terms of the b and c. That we have got the roots are actually given by alpha plus 1, beta plus 1, and the gamma plus 1. From there, okay, we just need to let the new variable, okay, to be the new roots there. And then we will just make like either the alpha, beta, gamma to be the subject, and then we just have to substitute in. So once we actually substitute in, right, there are actually quite a bit of things that we need to tidy up, okay, because they are actually all in terms of like we have got a lot of the constants there, the b and the c there, okay. So once we actually tidy up, this is the equation that we are getting, which has a lot of like the c's and the b's there. So so in the next part, okay, it is given that we have got the gamma plus 1 is a negative alpha minus 1. So deduce that we have got this relationship here. So basically sometimes when we want to prove this kind of the relationship, right, we might not have any idea like how do we actually prove this kind of the thing. But the trick is that, okay, you could actually look at like, you see what is actually needed in this case here. So we can actually observe that these all these constants here are actually the coefficients of all these here. So it means that we are trying to relate, okay, them. So when we actually say that we want to try to relate them, it's of course that we just write out every single thing, and we just list out. So for example, like, okay, for the new equation that we have here, we have got the sum of their roots. Okay, so this is the sum of their roots is negative b over a. And from there, right, okay, we are using this relationship to sort of reduce our thing a little bit. So in the sense that the lambda plus 1 here could be written as like a negative of the alpha plus 1. So when we actually replace the lambda plus 1 here with the negative of the alpha plus 1, we only have this, okay, beta plus 1 is this the negative of a b minus 3. So other than that, okay, do the other thing. So is to find the sum of the alpha beta. So just list out every single thing there. So we know that this is equals to like the c over a. So the c value that we have in the equation here, sorry, I forgot the y. So the equation here is that we have got this, okay, c minus 2b plus 3. So with the same relationship that we actually substitute in, so we replace the this one, the lambda plus 1 with the negative of the alpha minus 1. So for this one, we don't go and like disturb it. So at last, what are we getting here is just that we get the alpha plus 1, gamma plus 1 is this. So what is actually the b and c last? Okay, at the last part there. So of course, it's the sum product of all the roots. So the product of all the roots. So when actually multiply this product of the all the roots here is to look at I've got this relationship multiplied by this relationship here. So we can actually write it here. Okay, and we know that okay, the product of all the roots is actually like negative d over a. So we actually have got like a negative of the d over a from the equation. So we can actually like cancel the negative off, and this is how we could actually prove this relationship here. Okay, it's to link all the values that we know here about all the roots together. Okay. So for the question for this is not something that is like very uncommon. It's the divisibility. So we could, okay, first is to start with like, okay, we have got 7 power 2m minus 1. Then it's to prove for all the positive integers n here. So with that, okay, we just need to like do the first case. The basis case is to sum in the n is equals to 1. So we found out that, okay, it is actually a 48. It might not be clear if you just leave it as like a 48. So like I said, it's always that we could actually factorize the 12 out so that we know that, okay, this is really divisible by 12. Okay, this is when we prove the first case. So as we prove the PK, okay, so this is some usual step. So in my case here, I actually let this PK, which is a 7 power 2k minus 1 here, to be equals to 12c, okay? Because when we say that this is divisible by 12, it should be able to like express in the form of like a 12 multiplied by a c here, but we need to specifically mention that the c here must be an integer. It cannot be any other thing. Okay, if it is a fraction, then it doesn't mean it is divisible already. Okay, you must actually indicate this clearly. So now, okay, it's to prove for the case for the pk plus 1. So for the pk plus 1 is, okay, we replace the k plus 1 into the, no matter it's the n or the k there, and then we just need to try to split the terms from there. So from the 7 power 2k plus 2 here, we just need to split the terms until we get like 7 power 2k. So this 7 power 2k here is multiplied by 7 squared. Okay, so for this 7 squared here, it's actually the 49. So for the 49 of the 7 power 2k here, we split them. One of the 7 power 2k, we pair that with like a -1 here. Another one, we will just leave it there. So we have got like 48 dot with the 7 power 2k. So from our previous assumption there, so this is actually can be written as like a 12c. So from there, at the end of the all the steps here, we are actually able to factorize out the 12, and then we actually have something like this. So we can actually add on something and say, okay, this is divisible by 12. Okay, so after that, we can actually prove that the pk plus 1 is true, and then the conclusion here is we just take what we have from the question there. Okay, this is very easy to do. Okay, next question. So by simplifying, okay, we have got this thing here, show that this 1 over x power n thingy is equals to the negative x power n, and we have got so many square roots here. Okay, so what do we need to do from there is just, okay, we can actually observe that this is actually like a minus b, and this is like a plus b form. So at last, it is giving us an a squared minus a b squared form. So it is actually very nice. It will actually be reduced to a -1. Okay, so from there, okay, I didn't really work out everything from there, but you just need to like move around, okay, from here, then you can actually prove that you have got like this part already. Okay, they didn't give much space here, just doubt like why. Okay, but you need to like move around first. Okay, so this is our UN. Okay, so we need to use the method of differences to find the sum of the UN from n equals to 1 to capital N in terms of the n and x. So of course, I mean, the way that they actually like design the question, they won't purposely like ask something which is unrelated. Okay, so it's to use something that is actually like kind of a related from there. Right? So what we can actually do from here is that, okay, because we see this is what we actually have in the expression there. So we can actually use the result from the first part there, okay, to actually replace it here. So from there, we actually have got, okay, this is it, okay, the original terms there, and then this is what we have actually replaced. So we can actually factorize out the negative from there. Okay, we can actually factorize the negative from there, so that we get like this is a plus and then this is a plus. So it's like a whole set, two terms is a whole set like that. So for this, you could use the FR plus 1 minus FR, but I guess the more straightforward way for us to actually work on that is that we list out the terms. So we can list out like the n equals to 1, n equals to 2, of course like the last two, n equals to capital N, and then n minus 1. Okay, so with that, we just need to see how the terms can actually cancel. So the terms cancel like that. Okay, wait, sorry, I draw like one extra thing there. Okay, so the terms cancel like that. So the remaining terms, we just need to actually write them down. Okay, so always list down the terms. That would be, I mean, we can use the FR plus 1 minus FR if you want a quick result. But I guess, wait, I got some. Oh, okay. This thing here, right? Okay, it is that we have to list down the terms. Okay, it's the clearest that we could actually show. Okay, so just list down the terms whenever we see this kind of question here. Okay, the sum of the method of differences and FR plus 1 minus FR, that thing is to help us to get the result quickly. Okay, so deduce the value, okay, in which the infinite series is convergent, and find the sum to infinity when this exists. So what we actually have in this is that, okay, they are actually adding the u1 until the u infinity. So it means that, okay, when we add the u1 until the u infinity, it means the capital N here is an infinity. So we have to look at, okay, what are the terms that is affected by the capital N then? This is affected by it, and this is also affected by it. So when when we have got the n is actually like approaching infinity, and it is actually like a power of the x, right? I mean, this is some quite common question that they might ask. Okay, in fact, they actually asked it a few times in the past year. So this is a very useful result whereby if we actually have got, okay, they want us to deduce the value of the set of x, right? It's convergent. Convergent means it won't go to infinity. We have, okay, when the x is a value which is in between -1 and 1, then when we have got the x power n, right, it will actually be approaches 0 as the n here approaching the infinity here. Okay, so from here, what are we actually like looking at is this power m plus 1 and power m plus 2. So those terms will actually just like approaches 0 as the n approaches infinity. So this is what they actually want to look at. Okay, you can see how many marks for this question. It's a 3 marks here. This is 1. Okay, and then the answer is actually 1. So what are the terms that is affected? Is all those terms that has like an x power n, this thing. Okay, so another mark, okay, will be given like when we actually sort of like try to explain when like this is actually approaching infinity. Okay, so at last, just like all these terms becomes a 0, it actually gives us a result. So the result actually looks like this. Okay, when an n, I mean the capital N approaches infinity here. Okay. So, okay, this is about the transformation. We have got two matrices here, matrix A and matrix B. So we need to explain, okay, what happened in the matrix A here. Matrix A is a reflection in the line which is like y is equals to x. So again, it's always to look at like the images. Okay, for A, 1 0 becomes 0 1, and then 0 1 becomes 1 0. So this is when they actually interchange their position. So this is the reflection, okay, in the line which is like y is equals to x. For the matrix B here, we don't need to think much. Once we see this kind of the matrix, then we know it's a rotation already. Okay, so also like try to memorize the matrix for the rotation. So we don't need to derive on the spot. Okay, so many things to do. So when the negative is actually here, it means it is anti-clockwise. So we just need to compare, okay, this matrix with what we have in the cosine thingy here, and we can actually solve for the data. So basically, this is a rotation, okay, where the angle and then the direction is anti-clockwise. So not just this, okay, we need to actually ensure that we actually mention about the center, because we might actually rotate it in a different point. So, but in our context, our all the this kind of the transformation, right, is actually about like the center above the origin. Okay, so we must always mention about like center above the origin. Okay. Okay. So the next one is, okay, triangle DEF is transformed by the AB onto the triangle PQR. So show that the triangles DEF and PQR, they have the same area. So this is about the area. So whenever we talk about the area, it's always about the determinant of the matrices. So now we are using the AB to transform, okay? So for that, we need to find out what is the AB. We need to use some matrix A to multiply by the matrix B. So this is the matrix that we get. And what happened is, okay, we can actually find the determinant of the AB. So here, the determinant here is a -1. So this is, okay, this is how they give the marks here. One mark for getting the AB, another mark for getting the determinant of the AB. And then the last one, you need to explain why do they actually have the same area. So even though the determinant is a negative, but it doesn't matter. It is just like this -1, when we consider the modulus of it, it is actually the scale factor of the area of the transformation. Okay, so after that, then we can say that, okay, these because the area of the PQR is this modulus of the -1 multiplied by the area of the DEF. So in that case, they will actually have got the same area. Okay. So the next one, find the matrix which transform the triangle PQR, okay, onto the triangle DEF. So earlier on, we were using DEF to transform to PQR, okay, by using the AB. So if it is the other way around, then we need to find the AB inverse. Okay, since we already found out what is the AB inverse already, then we could actually like find this matrix very easily here. Okay, it's a 2 by 2. Just use the formula for the inverse to actually find that. Okay. So for the last part E here, it's about like finding the invariant line. So to the origin. So usually they will just ask for to the origin. So it's a usual step. Okay, we let the AB multiply by the xy, we get x1 y prime. And then we just try to multiply, relate them by using the y prime is equals to mx prime, as well as in the middle of the step, we relate that with the y is equals to mx. So at last, it will give us just a quadratic equation, which is in terms of the x there. Okay, which we could actually try to solve it. In this case, okay, you can actually use the quadratic formula, or if you want to actually do the complete the square, okay, by all means, feel free to do that. So this value of the m here doesn't give us quite a nice value, okay, unlike the questions that we have seen before, okay, it gives us something like a search value. So no matter how, okay, we can actually solve it in exact form. And then the thing that we need to remember at last is that we always need to restate, okay, what are the equations of the lines. So we can't just stop at the gradient and assume that we already know what is a line. Okay, always restate what are the equations of the lines then, right? Okay, so next. Okay, this is the ln of a 1 plus pi minus a theta. So sketch C and state the polar coordinates of the point of C, which is furthest from the pole. So this is the question type that is like the first question they already asked us to sketch. So it shouldn't be something that is super difficult to sketch. It's either they will give us some usual trigo functions. Okay, so we know how to actually sketch for the trigo functions. In this case, it's a ln. But we can actually see from here, okay, they must be monotonous, as in, because this data, right, has got a negative term. So it means that from the 0 to pi here, as the data increases, the r will actually decreases. Okay, so the r is actually getting smaller and smaller. And in fact, okay, because this is the property, right, we just need to look at the endpoints. Like when data equals to 0, the r here is a ln 1 plus pi. So this would be the part that we actually have got like the largest r. And when we have got the theta equals to pi here, the r is actually like a 1, the r is actually like a ln 1 plus a pi minus a pi, which is a ln 1. Of course, it's a 0. So we know that this is how the curve would look like. It will go to a 0, and then the starting point is actually here. Okay, so you could actually mark the intersections here. Okay, so this is a 0 here. So you need to state also, yeah, because the question really asks us to like state the polar coordinates of the C, which is furthest from the pole. So it is not like stating the largest value of the r. Okay, we need to have the polar coordinates. So make sure it is really in the form of the r and the theta. So when theta equals to 0, the value of the r here is a ln 1 plus pi. Okay. So the challenging part, okay, would be the part which is they show it like this here. So using this substitution, the u is 1 plus pi minus theta, or otherwise, show that, okay, the region enclosed by the C and the initial line is something like this. Okay, a bit of work to do. This is u, okay, and then we need to actually get the du d theta. So it's a negative 1, so the du is a negative d theta. And after that, what we actually have is, okay, when we have got the values, okay, so this is to integrate from 0 to pi for the theta here. So we need to change, okay, the value. So we get like the u is a 1 plus pi, and then also we have got the u is a 1 here. So when we actually look at the area, which is a half r squared d theta, okay? So d theta is a negative du, and then this whole thing inside here is a u. So basically, we actually integrate a ln u squared. So again, these limits here, yeah, the 1 plus pi and also this 1 here, right, it must be correspond. Okay, when theta equals to pi, the u is a 1. When theta equals to 0, the u is a 1 plus pi. So because of the negative here, I can actually switch. Okay, so you can see this is what I actually get from here already. Okay, and after that, right, we are integrating a u squared. So this is not some usual substitution that we're actually doing. Okay, so here we need to use by part. So in this case, for the by part, I actually change the variable a little bit. If we still use a u and a dv, it will be very confusing already. So I'm using, like, say, the p and q. So this is like the du where we have to differentiate it. This is like the dv dx that we need to integrate it. Okay, differentiate ln u gives us a 1 over u. Integrate a ln u gives us a u ln u minus u. Okay, so for this, for this we should have like a bit familiar, okay, on how to actually integrate the ln x. But if you are not sure about how to integrate it, just do another round of the bypass to integrate the ln u from there. Okay, so it's actually quite a bit of work that you need to be careful. So this is like our uv multiplied together, and then we have got like this is like a v v du. So when we have the v du, the 1 over u to multiply by this whole thing, we get the ln u minus 1. So the headache part is to sub in the values. Okay, it's a bit headache. But the good news is when we sub in the 1 inside all these, the terms are actually gone. So we are only working with like 2 terms only when we sub in the 1 plus pi. Okay, we sub in everything here. So make sure your brackets are enough. Okay, so this is when we actually evaluate the first part there. Second part, okay, we are integrating the ln u minus 1. So when you integrate ln u again, it's a u ln u minus u, and then minus another 1 here is like a u again. From here, sub in, okay, and we actually get all this. Just be careful, like with all the brackets there whatsoever. Okay, so it's a lot of things. So just be careful on all the brackets there. So after that, it is to actually tidy up, okay, and you should be able to actually get some expression which is like this. So it's a bit headache, okay. You see there's actually quite a lot of the terms here. Then you really have to simplify carefully then, okay. So this is the question that worth 6 months. Okay. Right, so let's look at the next one. So another calculus question again. Show that the point C is furthest from the initial line. We have got something like this here, okay? So, and then verify this equation has a root in between 1.2 and 1.3. So, this is the y is equal to r sine theta. So again, initial line is this one. The furthest point is to actually find the maximum of the y here. So we need to have an expression for the y here. So it's a combination of this. The r is a ln function, and then we have to multiply by a sine theta. So we need to find the dy theta here, which is not too bad at all. It's not difficult for us to actually differentiate. Just that one dangerous part is that when we differentiate this ln, right, you need to have a negative here because the coefficient of the theta here is the negative itself. So you have a negative here. The rest of it is just as usual. So when we have got the dy theta is actually equals to 0, okay, so what we have is we just have to rearrange. Then we can actually get what do we want to prove in the question there already. After that, okay, is to use the sign change rule. Okay, so we let the f theta to be that equation left hand side, and we use the sign change rule to prove that they have got sign change, or we say that they have got like opposite sign, things like that. So we can actually prove that this equation has a root which is in between the 1.2 and 1.3. So you need to remember lah when we actually use this in like a differentiation integration, right? It must always be like using the radian. Okay, please set to the radian mode first. Okay, then only we can actually like get the correct values here. Okay. Okay, so this is the question. That is rational graph. First curve is actually not really a lot of the issue here. Basically, we just need to know how to change it to the partial fractions, okay, and then we can actually sketch it very easily already. This is when we have got like the asymptote y equals to 1, the x is equals to 2a. Sorry, this one is a 2a here. Okay, so we can actually get the graph which is like this here. So the curve C2. So for this curve C2 here, we have got the equation, okay, which is like the x minus a over x plus 2a squared. So we want to find the stationary points of the C2 here. So what I'm actually trying to do here is that I am not going to expand and use the quotient rule for now. What I'm trying to do is I'm trying to differentiate this as like some function that has like a power here. So what I did was bring down the power this thing becomes power 1. And later on, we need to differentiate whatever which is inside the bracket, right? So if you look at this expression here, if you want to differentiate it, we might need to use the quotient rule. But I actually use the other form of it because the x minus a over x minus 2a is something like this, right? If I actually differentiate this instead of the original things in the bracket here, this thing here is much easier. So you see how when we actually differentiate that, right, they actually have got some common denominator that we can actually multiply them together. And this is actually quite nice. That we can actually get dy dx in this form. Which later on, so easy that we can actually equate the dy dx to 0. We are just looking at the numerator. So it gives us that the x is equal to a. So we know that when x equals to a, the y is equal to 0. Okay, that's a turning point there. Okay, so in the part 2 here, it's another thing. Okay, it's another thing. So if we want to find the intersection, so we are actually solving for like the square and also the modulus of it. So the first step that we can actually know is that, okay, we are going to open up the modulus and it will become like a plus and minus. Okay. For this, of course, yes, we are considering two different cases where it is actually a plus and a minus. Okay, it is a plus and a minus. But what are we actually doing here is, okay, we are not going to cross multiply. If you cross multiply, you will end up with a lot of the cube terms. Then you have to cancel it's a pain, okay, when you want to cancel later. The approach that I actually use is that, okay, you imagine this is like some y, right? So I'm looking at like y squared is equals to a plus minus 1. So when I want to solve the equation here, I just need to look at like, okay, y squared, when we move that, it's also, let's say it's just a plus minus also lah. Okay, two cases now. Okay, so factorizing. Okay, like this, it's easier to solve. Okay, so this is the y log, and then we have got like this is y plus minus 1. So this is a y plus minus 1, this is a y plus minus 2. In that case, because the denominator we don't need to care about it now because it's equals to 0, right? So we just need to look at the numerator. So when we have got this form already in the numerator, it's even easier. It's already sort of like in a factorized form. So we don't need to actually like factorize it again later on. Okay, this approach is much easier and organized. Okay, and the other one is the same thing. So you just have to look at like the numerator because the denominator we don't need to really care about it, right? So after that, we have one solution for the x equals to a, and then we also have got like x equals to 3 or 2a. So basically, there are just two values lah, which is the the x equals to a, y equals to 0. And for another one is when x is equal to 3 or 2, sub in, and we can actually get the value of the y here. Okay, so you see it's so nice, okay, that we can actually get these solutions here. Okay. Sketch the C2 and C3 on the single diagram, okay, identifying each curve. Hence, find the set of the values of which, like we have got the C2 is actually less than or equals to the C3. Okay, so we look at the situation here, yeah? Okay, this is C2, this is the C3, right? So, which one is actually easier to sketch? The answer is the C3. Okay, because C3 is just, what is that? Okay, we just reflect. Okay, so we can sketch the C3 first. So you can see the green ones here are C3. Okay, so now let's look at the C2. So what happened in the C2 here is that you just need to imagine when we actually, okay, even when we actually square this, right, we are also getting this value here also. Can you imagine that? Even this one is without the modulus, we can square that, so we can actually get this. Okay, but even with the modulus, we square, we are also getting these values here because all the squared values are positive. Okay, so it means that if you actually draw the C3 curve here, it's easier for us to actually draw the C2 because we just need to square whatever that we have in the C2 here. Okay, so for instance, this is our C3, right? And when we square the values for this one, it's giving us a C2 log. So you can see the C2 for this part here is higher than the C3 because we are squaring those values from the C3. So we get the C2 curve which is higher than it. Okay, so remember the thing that we actually like learn for like the y is equals to y squared is we actually square that. So what happens is that, you see, okay, if the green part here, okay, let's look at from here onward. This one. If this is our C3, when we square that, we will give a curve which is higher. So the C2, you can see it should appear higher than the C3 here. Okay, because what we are squaring was the area, the value which is greater than 1. Okay, so when we square those values, the C2 actually gives us a higher value, which is where in the previous part of the question, right, they also sort of give us a hint already. So they should intersect at this point. So from there, they should actually intersect at this point here. This is the 3 over 2a and then a 1. Okay, so they should intersect there. So other intersections here is actually like an A0. So why do we have like an A0 is because if the original C3 is 0, C2 should be a 0 as well because we square the 0. So this is why they have got this intersection here. Okay, and then we look at the C2 and the C3. For the part where we have got the y is in between 0 and 1, right? The C3 should be higher than the C2. Because you imagine, if this is a value which is say, like let's say just simply saying, okay, it's a 0.5 on the C3. If C3 is having the value of the 0.5, C2, which is like the C3 squared, right, is actually having a much smaller value. So this is why in this region here, from the 0 to 1 for the y, right, the C2 should appear lower. Okay, it should appear lower than the C3, but they have got one intersection point here. Of course, this is when they have got the 0. Okay, so this is how we can actually like construct this curve here. Okay, and then after that, okay, we need to find, okay, the part where the C2 is actually less than or equals to the C3. So C2 is less than or equals to C3 is actually when we have got from here onward. This all part here. Okay, so we just need to state the inequality, which is that x is less than or equals to 3 over 2a. Okay, so to be honest, this question is not so straightforward. Right, so this is the way that we actually tackled it with a little bit of the technique, so that we, we don't actually like jump into the trap that they might actually trick us with a lot of the algebraic work. So with a bit creativity, you can solve these questions with much elegant. Okay, so no need to like sketch, no need to like square everything here, and then you will end up with like super long working here. This is a nice and elegant way of doing it. Okay, right. What else do we have? Okay. So surprisingly, recently the vectors question is not something that that they're actually playing with. In fact, the vectors question that I have actually seen in these 2 years are actually like quite straightforward. Okay, let's look at this. This is we have got 3 points, okay, and then they actually give us like the ABC, okay, then they ask us to find the equation of the plane ABC. So this is actually like similar to the question in another variant. So they actually like ask the same types of the question. For the plane ABC, so what we need to do is just we need to take any 2 vectors, anything you like, A, B, B, C, any 2 combinations, we just need to cross them. So when we cross them, we are getting a normal. So with the normal, we use the r dot n is equals to a dot n to actually like get the equation of the plane there. Okay, straightforward. Part D also, they ask a similar thing as what we have in the other variant there. Find the acute angle between the OBC and the ABC. So basically, is to find the angle between the normals. ABC, we have got the normal already earlier. We just need to find the normal of the OBC. So for the plane OBC, we could actually cross the OBOC. Okay, OBC, we just need to cross the OBOC because that is the easiest one for us. We don't need to do anything. So we get this normal. So using the normal from the 2 planes, we just have to do the usual dot product, and this is what we get. Okay, like that only. Right? Okay. Okay, so this is something not so difficult as well, just that there is a little bit of the algebraic work that is involved here. Okay, so the point D has this position vector which is called Ti and also minus j. So the shortest distance, okay, between the lines AB and CD is a certain, find the value of the t. So here they mentioned about the shortest distance between 2 lines. Okay, so we just need to look at the equation of the line first. Okay, we didn't do the equation on the line first, right? So we need to actually do it here. So it helps us in identifying those vectors clearer. Line AB, just take any point, okay? AB, okay, A or B here, and then this direction here is we can use the vector AB that we have earlier. Okay, so CD we need to find a little bit, so we could actually use like the OD minus the OC here to actually get the direction of the line CD, which could be the vector CD itself. Then we form the equation of the line CD. So after that, just recall the formula. The formula is point minus point, direction cross direction. So when we cross the direction, it's a bit of like the things which is in terms of the T already. So after that is to put them together. So this is the point minus point. This is the direction cross the direction. We dot them. We put the modulus to it because we just want the distance there. Divide by, okay, so what do we divide by here? So we divide by the magnitude of this, the cross product here. Okay, so we can tidy out a little bit there. Must be a lot of things which is like in terms of the T here. Okay, but it is actually not too bad when we actually like try to square both sides and we try to solve them, right? The T square term will actually get cancelled off nicely. So we only have like one value of the T for us to actually worry about in this case. Okay, so it's actually much better than I imagined for the algebraic work that is actually involved here. Because most of the time when they ask this kind of question, right, there would be two values of the T one. Okay, this is like quite nice. Okay,